In this video, I'm going to set up and solve exercise 10.46 from the back of your book. It's about a diver on a diving board. You're told that you have a diving board that's 3 meters long and that it's supported at 2 points, and at one end there's a diver. So at the left end, there's got to be something to hold the diving board down. So I'm going to just draw a downward force here and call that F1. And then 1 meter over, there has to be an upward force to prevent the diving board from going down. So I'm going to draw that one here. And I'll just label that F2. And then you have the diver out at the other end standing on it. And you're told that her weight is equal to 500 newtons. And lastly, we can't forget about the diving board itself. It has a weight of 200 newtons, and you're told that it's a uniform diving board, so you can put a 200 Newton weight right at the center of the thing, or 280 newtons. So these are the forces that are exerted on the diving board. Now we can put some distances to locate everything. First of all, the entire diving board is 3 meters long. So that would mean from here to the center of the diving board is 1.5 meters, because the weight vector is located at the center of the diving board. And you're also told that the support point is 1 meter. The two support points are 1 meter apart. So these two forces are a meter apart. The weight of the diving board's at the center of the diving board, and then the diver at the end is standing 3 meters out there. So this is a nice free body diagram. There's no forces to resolve into components. If we're going to do a coordinate system, I guess I would just do y is up, and there's really no need for an x because there's no horizontal components to this. So we could immediately see what the first condition of equilibrium has to say. If we sum the forces that act in the y direction, we get a truth. So I see 3 forces that are down, F1, the weight of the diving board and the weight of the diver, and 1 force that's up. So I would write F2, that's up, and then minus F1 minus the weight of the diving board minus the weight of the diver. It's got to give you 0. And keep in mind, this is 280 and this is 500. The questions are to figure out what are the magnitudes of these two forces, the forces that are exerted on the diving board by its supports. And you can see from the first condition of equilibrium, we have an equation that has 2 things we know, but 2 things we don't know. So we can't solve it. We need to resort to torques, the second condition of equilibrium. So we're going to sum the torques and set that sum equal to 0. But like before, we have to choose an origin in order to calculate a torque. Now, there's no rule about where to choose the origin. You can choose the origin anywhere you want. Normally, you pick a place that eliminates one of the forces that you don't know, so you end up with an equation that you can solve. So thinking ahead, I could pick here as the origin. Then F1 would not exert a torque because it's exerted at the origin, but F2 would, and the 2 weights would. Or I could pick here and use this as the origin, because then F1 would exert a torque, but F2 would not. So I think if you did this problem, you would probably pick the left end, and that's totally fine. In fact, I'm going to pick this point as the origin and solve it like that, and then if you want to solve it picking this point as the origin, you can do that and see that you get the same example, same answer. So I'm going to pick the origin here, and I just have to account for the torques exerted by the 3 forces that aren't acting at the origin. And again, I got to make sure I include their direction with a plus or a minus sign. So let's take the torque due to force 1 here. If the board pivoted here and force 1 pulled down, the board would rotate counterclockwise. So that torque is going to be a positive torque. The magnitude of the force we don't know, but the moment arm we do. It's 1 meter. So I'm going to write plus F1 times 1 meter. So that accounts for the torque due to this force. This force doesn't exert a torque because it's exerted at the origin. There's no moment arm, but this one does. So if the board pivoted here and this vector pulled down, that would cause the board to rotate clockwise. So a clockwise torque is minus the weight of the board, but the lever arm, you see, is only this distance here. Since the board is 3 meters long and the weight acts at the halfway point, as we decided before, the lever arm here is only 0.5 meters. And lastly, we have to account for the torque exerted by the diver at the end of the board. So that'll be minus the weight of the diver times that lever arm. Don't jump to the conclusion and use 3 because I'm selecting the origin here, so we need the distance from the origin to where that force is exerted. So that's only 2. So that's got to give you 0, and that's another truth of the system. But this one I can solve because I know the weight of the diving board, and I know the weight of the diver, and I know all the moment arms, so I can solve that one for what F1 has to equal. It'll be the weight of the diving board, which is 280 newtons, times 0.5 meters, the lever arm, that's this one, added over to the other side, plus 500 newtons, the weight of the diver times its lever arm, 2 meters. And then, although it doesn't matter in this case because the lever arm is 1, to get the units to work out, I got to divide it all by 1 meter. So basically, I solved equation 2 here for F1 by plugging in the numbers. And so if you blast through this, you're going to find that F1, I think, is 1140 newtons. And then how would we go and figure out what F2 is? Well, we can go back to equation number 1 because we now know that F1 has got to be 1140 newtons. So F2 is, solve this for F2, you're going to end up with this on the other side, this on the other side, this on the other side, all plus. You just got to add them all up. And I think you end up with 1920 newtons. So that's how you would solve this problem using the first and second principles of equilibrium, conditions of equilibrium, choosing the origin to be this pivot point here. What might be a good idea for you to do is to solve the same problem, but choose the origin to be here, and see if you can account for the lever arms properly and show yourself that in fact you get exactly the same answers.